All right, here's the beginning of integration. And so I think I mentioned it briefly in class before. The idea is integration is a funny word, but it implies actually taking antiderivatives. We've been taking derivatives, now we're going to undo them. Take antiderivatives, and one of the synonyms, and there's probably deeper meanings we can dive into later, but really integration is anti-deriving, undoing derivatives. There's great conceptual applications, kind of like taking derivatives gave us rate of change. Taking antiderivatives is going to give us area or accumulation under a graph. So we're going to apply this in different ways down the road, but right now it's just getting into the nitty-gritty of how to interpret it, how to read it, how to do the basic antiderivative techniques, and that opens doors to all kinds of cool processes. So just kind of make your way through this, and of course you can Google 100 different ways to look at this, but this will give you an idea in the context of how we'll tackle it in class. Basically, the antiderivative is one way of integrating. We will put out, here's y equals 5x to the sixth. Let's work with what we know. We know how to derive this. So let's take the derivative of that, dy dx, and that's 30x to the fifth. You bring the power out front, multiply it, and then reduce it by 1. So we're all pretty comfortable. It's called the power rule. Now, the thing is that what I can do is I can say, if the derivative of y equals 5x to the sixth is 30x to the fifth, then I can say the antiderivative then of 30x to the fifth is 5x to the sixth. So the problem is that actually there's a little more flexibility to this. It's not the antiderivative, it's an antiderivative. Let me give you an example. So if I give you another example of y equals 5x to the sixth plus 3, and I say get the derivative of that, then dy dx is 30x to the fifth. Same thing, because remember the derivative of that 3, that plus 3 is 0. So we have two things that give us the same derivative. So now when I say, the antiderivative of 30x to the fifth is 5x to the sixth, I have to be more careful because actually the antiderivative of 30x to the fifth is also 5x to the sixth plus 3. So to say I'm going backwards. So antideriving is undoing the derivative and going back. We have two different things that are the antiderivative of 30x to the fifth. Sounds confusing, but not really. It's actually just a generalization we can make. So let's talk about what's going on in general. So here's what we've been dealing with, right? So we got these 5x to the fifth. 30x to the fifth is the antiderivative of that is 5x to the sixth. So is 5x to the sixth plus 3. Okay, so we got two options going for us. So we have an antiderivative. Well, there's a generalization that I can make about this. What about plus 17? 5x to the sixth plus 17. If I take a derivative, I would get 30x to the fifth. That means, hey, we get another one. 5x to the sixth minus 35, take the derivative of that, I get 30x to the fifth. Yet another example. So if we make a little list here, we've got now 5x to the sixth plus 17, 5x to the sixth minus 35. The derivative of each of those is 30x to the fifth. Therefore, an antiderivative of 30x to the fifth is all kinds of stuff. But see if you can pick up the pattern and see if you can find a fun way to generalize this. Okay, so let's write down our list of current antiderivatives, okay? So if I keep going, here's what I can get out of this. If all of the current antiderivatives of 30x to the fifth are 5x to the sixth, 5x to the sixth plus 3, 5x to the sixth plus 17, and 5x to the sixth minus 35, what we notice is when we take the derivative of each of those, the constant goes away. So it doesn't matter what the plus constant or minus constant is. So we can just say, hey, 5x to the sixth plus c, that's the antiderivative of 30x to the fifth for any constant that you would put in there. So we have this plus c because it really is the derivative of 5x to the sixth plus any constant is 30x to the fifth. Therefore, the antiderivative of 30x to the fifth could be any 5x to the sixth plus c under the sun, whatever c happens to be. Now, there are ways of finding out what c is under certain circumstances, but nothing we need to worry about right now. But we do need to be accurate when we say the antiderivative of 30x to the fifth is, you got to put in a general 5x to the sixth plus c, because it could be any plus c, or any minus c for that matter. Okay. So now let's talk about something called, oops, I changed orders here. We're going to do the notation of integration so that you can see there's kind of a shorthand that says you are going to take the antiderivative rather than the derivative, because by the way, they do get mixed up in our brains if you're normal. If I am going to take the antiderivative of 30x to the fifth, like I've been doing, this is the notation that goes with it. Looks really fun. It's the kind of stuff you see in the back written on the wall and behind any major movie that has mathematics in it. They love to throw integral symbols in there. Or Peg plus Cat, an awesome PBS TV show. She's got integrals and summations all over her particular show. But here's what I've been doing, by the way. We're taking the antiderivative of 30x to the fifth, and we're getting 5x to the sixth plus c. Let me translate that. So we also call it the integral of 30x to the fifth is 5x to the sixth plus 3. That's a notation. That's that word integration or integral that I've been mentioning along the way. That's what this notation looks like. Also known as what we've been doing all along, the antiderivative of 30x to the fifth is 5x to the sixth plus c. All those are accurate statements right there, and they're all synonyms. The symbolic one on top, the integral, using the word integral, or using the word antiderivative. They're all synonyms and all accurate ways of describing what's taking place there. So you got to get used to that. And don't forget, now we always want to keep this in mind, what that means is then also the derivative of 5x to the sixth plus c is 30x to the fifth. Because remember, an antiderivative is undoing the derivatives we've been doing all along. And we all know the derivative of 5x to the sixth plus a constant is 30x to the fifth. Therefore, the antiderivative of 30x to the fifth is 5x to the sixth plus some constant. All right, so here's the big theory, though, too, that's going to play out in multiple ways, but let's just keep it pretty simplistic at this moment. Derivatives and antiderivatives are inverse operations that undo each other. They're kind of like multiplication and division, exponents and logs, and a number of other inverse operations we've encountered. Sine, cosine, tangent in their arc, sine, cosine, and tangent, inverse operations as well. So here we are. Let's talk about a little bit more about this notation. There's names of these things. So the little kind of a slender s you put up front, it's called the integral symbol. It really is a shorthand for a summation of something, and that's something, again, we can elaborate on later. It really is kind of like an S for summation. And we call it the integral symbol. Then the thing you're integrating or taking the antiderivative of is called the integrand. And then the dx is the with respect to x. It's actually the same thing we did with derivatives. We take derivatives with respect to t or with respect to x, and we had a dx or a dt respectively. It's the same thing, but it's notated a little differently. It's in a different position. So just let's look back at the last time we used what's called differential notation with that dx in it. If y equals 5x to the sixth, then dy dx, the derivative of y with respect to x, is 30x to the fifth. Okay. Well, the thing is we're seeing that same notation pop up here. It's called, this is differential notation. And if you want to take a note, integrals, kind of multiplied by dx in this integral symbol here, and then derivatives we divide by dx. That implies that inverse relationship that exists between integrals and derivatives. And there's much more you can dive into that. There really is kind of an algebra and a mathematical explanation of why one's multiplied by dx and one's divided by dx. But those are just notations. Okay, the power rule of integration is your gateway to a lot of cool things to antiderive. It's like the power rule of derivatives, but really it's backwards. Instead of multiplying out front and subtracting 1 from the power, we end up adding 1 to the power and then dividing by it. But let's just pick up on that pattern here for a minute. Okay, here's what we know. The integral or antiderivative of 30x to the fifth is 5x to the sixth plus c. If you take the derivative of that result, you get right back to the beginning. They undo each other. You just work your way right back with a derivative. Okay? In a sense, you can check your answer. All right, if we have 24x to the fifth, the integral of that is 4x to the sixth plus c. So one of the things you want to get used to with antiderivatives, and I'll tell you the rule in a minute, no need to, other than just notating it and writing it down, you're just antideriving. Now, what you can do is, in your head if you want, what's the derivative then of 4x to the sixth plus c? Well, it's 24x to the fifth. Power out front and reduce it by 1. So we know it works, and sometimes that's enough for you to even do it in your head and come up with it. Do you want to try it on this one? Of course, you can pause this video at any time and give it a shot. Like, what would I have to take the derivative of to get 15x squared? What would I have to take the derivative of to get 15x squared? And if you're thinking about it, it seems like the power in antiderivative seems to go up by 1, so it must be an x cubed. And when you derive it, that 3 would come out front times some, maybe a 5 or something in front of there. Maybe you can kind of eyeball it and figure it out. It would be 5x cubed. Well, if you're good at picking up on patterns, or if you do this enough, you would get the pattern. It would become kind of necessity if you get inundated with a whole bunch of problems that are really repetitive, your mind, the natural curiosity and efficiency of your brain is going to say, what's the shortcut to this? And here it is. If you integrate ax to some n power, then you get a stays there. This is the constant multiplier rule kind of rearing its head again. A times x to the n plus 1 over that n plus 1. So think of how that's kind of the inverse operation of how we did derivatives, where adding 1 to the power instead of subtracting 1. Instead of multiplying by the exponent up front, we're dividing by it. So there's a lot of things that are similar, or ways that you can correlate to how it's the inverse operation. But that's your general power rule for integration. Add 1 to the power and divide by it. Any constants, just stay there. So here's one. Give a shot. If you want to think through it, I'm going to antiderive negative 24x to the 5th, and adding 1 to the power will be x to the 6th. That's the nice part. But we also divide by that 6th. Okay, so whatever you get your exponent to be, by adding 1 to it, you also divide the fraction by it. So 24x to the 6th divided by 6. This is accurate. That's the antiderivative. But we tend to, simplify down to something more simple. And the check, of course, is always, hey, is the derivative of that negative 4x to the 6th plus c really negative 24x to the 5th? And sure enough, it is. Okay, so you're undoing derivatives. Here's another. So 12x squared, if you integrate it, it's 12x cubed over 3. Add 1 to the power and divide by it. And you simplify if you can. And, of course, you can check it by deriving 4x cubed. And do you get 12x squared? Yes. And you move on. So these are just the habits, the process of, an antiderivative is undoing derivatives. There's some notation. The integral symbol is a symbol that says you're going to take the antiderivative of, work backwards. And, of course, you can check your work by deriving what you get to see if it matches where you started. And there it is. That's a nice start to antiderivatives. The next order of business is other integral rules, things that you can take antiderivatives of. We can expand your horizon quite quickly to more difficult antiderivatives with just a couple of quick tricks, and that opens up even more doors.